The last section we're going to cover in chapter 5 is section 5, the double angle identities. And unlike when we did the sum and difference identities in two separate sections, this is all of them are in one section. So I've written the double angle formulas on the board, which are in your notes. And the first exercise says, explain where these formulas are coming from. Well, let me start with the cosine. So notice cosine's a little different. Sine is equal to one thing, tan is equal to one thing, but cosine of 2a is equal to three different things. So I'm going to explain where all those are coming from. Well, let me start with, I'm trying to prove this identity, so what's the procedure? Start on one side and work your way to the other. So I'm going to start with cosine of 2a. But what is 2a? Well, 2a is just a plus a. A plus a is 2a, no problem. Now, why am I rewriting this expression in terms of this? Well, because now this looks like cosine of a plus b, which is something we did in a previous section, 5.3. Well, what's cosine of a plus b? If you look back at that formula, it's cosine a, cosine b, which here is also a, minus sine a, sine of b, which here is also a. So you're just going back to the cosine a plus b formula, but a is a and b is also a. Let them both be a. But what is this? Cosine a times cosine a is cosine squared a. Sine a times sine a is sine squared a, and we've got the first equality there. Cosine of 2a is cosine squared a minus sine squared a. Now I'm just going to continue on here. I want to show that this is also equal to this. Well, what's the difference between this expression and this expression? This has a cosine squared and a sine squared. This only has cosine squares. So we need to get rid of the sine squares and write it in terms of cosine squared. Well, if you remember, we had a Pythagorean identity. Sine squared a plus cosine squared a is 1. If you subtract sine square from, subtract cosine square from both sides, you get sine squared a is 1 minus cosine squared a. Okay, so we've used this before. So there's the identity we know. I made a new one from it. So sine squared is 1 minus cosine squared a. So I can replace sine squared with that expression, 1 minus cosine squared a. Right? So replace the sine squared with 1 minus cosine squared, and I still have the minus out front. Now if you distribute the minus sign and combine like terms, you get cosine squared a minus minus, that's plus cosine squared a, is 2 cosine squared a, and then minus 1. Right? So when you distribute, you get the minus 1, minus the minus is the plus, so you get cosine squared plus cosine squared is 2 cosine squared, and notice I've got the second one. So that's what I started with, and then I got it equal to that, and then I got it equal to that. Now there's one more left to go. I want to rewrite this in terms of make sure that these are equal. Well, it's the same idea. I need to get rid of the cosine square and change to sine squares. Well, if we do the same thing that we did before, but this time solve for cosine square, I get cosine squared a is 1 minus sine squared a. Subtract sine squared from both sides. And then replace cosine squared here with 1 minus sine squared. So I get 2 times 1 minus sine squared minus 1. So the minus 1 I left alone, the 2 I left alone, I replaced cosine squared a with 1 minus sine squared a. And if we simplify, if you distribute the 2, notice I'll get a 2 here, minus a 1 is a 1. Right? 2 times 1 is 2, minus 1 is 1. And then distribute the 2 to the sine squared, and you get minus 2 sine squared a, which is the third one. So all 4 of these are equal to one another. Okay, now let's move on to sine 2a. The first part is exactly the same as what we did here. Let me start with sine 2a. The 2a is a plus a. And now we're back to the sine of a plus b formula that we did in section 5.4, I believe. And so what was the formula for that? It was sine of a, cosine of b, which here is also a, plus cosine a, sine of b, which is also a. Notice multiplication is commutative, so cosine A sine A is the same as sine A cosine A, so you get sine A cosine A plus sine A cosine A is 2 sine A cosine A. And it pops right on out. So that is equal to that, which is what we were trying to show. And in the notes I didn't say to do this one, but it's very short, so why don't we do the one for tangent as well. Tan of 2A is tan of A plus A. 2A is A plus A again. But what was the formula for tan of A plus B? It was tan of A plus tan of B, which is also A here, over 1 minus tan of A, tan of B, which is also A. And if you simplify, tan A plus tan A is 2 tan A, and then 1 minus tan A times tan A is tan squared A, and that's the formula. So tan of 2A is equal to this. So they pop right on. These are special cases of stuff we did before, of the tan of sine A plus B, cosine A plus B, tan A plus B. Now let me briefly discuss how you use these. Okay, think about what the sine of A plus B, cosine of A plus B formulas did. If you knew about A and B, sine or cosine of those, it told you about sine or cosine of their sum or difference. What is this telling me? Suppose you didn't know anything about, you knew a lot about angle A, but you didn't know anything about double the angle for some reason. Well, if you know sine of A and cosine of A, it gives you sine of double the angle. Now be careful. You don't always have to have a 2 here. The way I always think of this is whatever angle is here and here have to be the same angle. They're both the same A. Whatever angle's here and here, double it goes here. Whatever angle is here, if you want to go this direction using the identity, half of this angle goes here and here. So for example, if I had 2 sine of 3x cosine of 3x, notice that this looks exactly like that side. The angle is 3x. So if I want to write it like this, that's going to be sine of double the angle, 6x. Okay? Or if I had 2 sine 4x minus 1 cosine 4x minus 1. Well, this looks exactly like this side. The angle A is 4x minus 1, so it's equal to this, which would be sine of double the angle, which is 8x minus 2. Okay, now that's going from this side to this side. What if I was going to go the other way? Suppose I had sine of 14y. Okay, so there's no 2 sitting here, but if I have whatever angle's here, if I want to rewrite it this way, it's the angle A is half of that. So this will be 2, it's always a 2. Sine of half of that, 7y cosine 7y. Now and the number doesn't have to be divisible by 2. Suppose I had sine of 3q. And I treat this as this side. Whatever angle is here, half goes here and here. So that would be 2 sine of 3q over 2 cosine of 3q over 2. Okay, everything doesn't have to be divisible by 2. It doesn't have to be even. Okay, so that's the way all these are working. Same thing here. Whatever angle's here and here, double it goes here. If you have this angle here, half of it goes here and here. So that's the way these identities are working. Okay, so the next example is just using these directly. It says suppose cosine of 2x is 0.3, and they want to know what's 2 sine squared of x. Okay? So they give you one quantity and they want to know another. Clearly, if they give you this and they want to know about this, there has to be a relationship between them. Well, we need an identity to relate to these two. Well, here's cosine of 2a, and there's sine squared right there. But here's cosine 2a, and here's sine squared. Now, which identity should you probably use? Right? You know this one, and you're looking for this one. If you use this identity, this equals this, you need to know something about cosine squared, and we don't. That's the problem with cosine 2a. You have to choose which formula is going to suit your needs best. So I'm going to use this formula, the third one here. So I'm going to say cosine 2x is 1 minus 2 sine squared x. I just recopied the formula. This equals this. Let's plug in what we know. I know cosine of 2x is 0.3. X is not 0.3. The whole thing. Cosine of 2x is 0.3. Right, so I just replace cosine 2x with what it is, 0.3. Now I'm trying to get 2 sine squared x by itself, so it makes sense to subtract 1 from both sides. If you subtract 1 from both sides, you get minus 0.7 is a negative 2 sine squared x. And a common question I ask at this point in this problem is, then what should we do next? And invariably, somebody will say divide both sides by negative 2. Because usually you're trying to get to, the part with the variable by itself. But remember what the problem asked for. The problem asked for 2 sine squared. So you don't want to get rid of the 2, you just want to get rid of the minus sign. So if you multiply both sides by negative 1, you get 0.7 is 2 sine squared x. So that's what they wanted. So 2 sine squared x is 0.7. Okay, so notice what this identity did for me. I knew something about this, and I wanted to find something about that. So that's that example. The next example, which is number 17. It says verify the following equation. Sine x plus cosine x quantity squared is sine 2x plus 1. And it says verify this as an identity. Now remember the procedure, start on one side and work your way to the other. And oftentimes I ask myself which sides are more complicated, because then it's easier to destruct than it is to start with something simple and construct. So I would argue this side is more complicated because you have a sum squared. You could also argue the right-hand side is more complicated because of the angle. I mean, the expressions are complicated, but notice the angle here is 2x and the angles here are x and x. So the angles over here are more complicated. So sometimes if the angle is more complicated, it may make sense to start with that side. But again, if you have an idea of where to begin, just pick that side and go with it and see what happens. If it works out great, if it doesn't, you can always start on the other side. I'm going to start with the left just because it is so complicated. And of course, the obvious thing to me to do here is to multiply this out. Sine plus cosine squared, if you FOIL that out, you get sine squared x. You get a sine cosine for the outside and a cosine sine for the inside, so you get plus 2 sine x cosine x. And then the cosine x squared is plus cosine squared x. Now, so it looks like we got a lot worse. And sometimes they do get a lot worse before they get better. But now we don't have a whole thing squared, we just have a sum of things. Well, do you have an idea of what to do next on this problem? There's 2 things. Again, always do one thing in each step, please, so I can follow your work. Okay? Well, one thing that catches my eye is I have a sine squared x plus a cosine squared x. Remember, that's part of one of our Pythagorean identities that we talked about earlier. Sine squared x plus cosine squared x is 1. Your eyes might not catch that because they're not next to each other. Right? But you can just say sine squared x plus cosine squared x is 1. So this simplifies to 1 plus 2 sine x cosine x. I think we're on the right track, right? We needed to get a 1 there, and there's where the 1 comes from. Now what about this mess? We have 2 sine x cosine x. We need to get to sine 2x. Why is that true? Well, that's our double angle identity for a sine. Right? 2 sine x cosine x is sine of 2x, so I can replace this second expression with sine 2x, and there we go. So it's not a very difficult problem. We'll do the same strategies we've done before. FOIL things out, Pythagorean identity. That should have been no problem. The only new thing is realizing that these are equal. You should get, you don't have to memorize the identities. You should get familiar enough with them so when they pop up in a problem, you say, wait a minute, I think that's one of them. Okay, so if you're not familiar with them, you won't even know to look. So that's that problem. Okay, the next problem has the same flavor as some we did in sections 5.3 and 5.4, where they give you information about one or two of the angles, and you have to find information about another one. So on this problem, they tell you cosine of theta is minus 12/13. They tell you sine of theta is positive, and they want to know what sine 2 theta And what's cosine 2 theta? Now again, what do you know about the angle 2 theta in this problem? What did they give you about the angle 2 theta? Nothing. It's not a trick question. They told you about cosine theta and sine of theta. You know nothing about angles 2 theta. Okay? You don't know where 2 theta is. You don't know the sine or cosine of it. But you know a lot about cosine of theta and sine of theta, not 2 theta. But to solve this problem, you need a relationship. You also need a relationship between sine 2 theta and theta, between 2 theta and theta. And that's what these identities do for you. Okay? So let's start with sine 2 theta. So I'm going to use the formula here. Sine of 2 theta is 2 sine theta cosine theta. Okay? So to find sine of 2 theta, I rewrite it in terms of theta, which I know a lot about. Okay? It's just like those sine of A plus B formulas. You didn't know anything about A plus B, but you knew about A and you knew about B, so you use an identity to rewrite it in terms of things you knew. So I'm rewriting sine of 2 theta in terms of thetas. Well, we were told cosine theta. There are two things to plug in here. So cosine theta is minus 12/13. Now be careful. I mentioned this in the previous section. Theta is not negative 12/13. Cosine theta. Do not write cosine minus 12/13. Theta is not minus 12/13. I have no idea what theta is. Now we need sine of theta. I know sine of theta is positive, but I need the actual number. Well, with this information, we ought to be able to draw a picture of theta. So if what quadrant's theta in? Cosine is negative and sine is positive. So in which quadrant is cosine negative and sine positive? Well, that's the second quadrant. I don't know the rotation. I'm just going to put something in. There's a picture for possible picture for theta. Always draw your triangles with a vertical line. And in cosine, well, what's the definition of cosine? That's x over r, or adjacent over hypotenuse. So the adjacent side is 12, hypotenuse is 13, and the negative obviously is on x. And to find the sine, I need the other side. This is one of our Pythagorean triples we did on the first day of class. If you have a leg of 12 and a hypotenuse of 13, the other side is 5. Again, you could use Pythagorean theorem if you didn't remember that. And obviously this side's positive, y is positive. All right, let's look at the picture. What's sine of theta? Sine is opposite over hypotenuse. So it's 5 over 13, and you should simplify your fractions. How do you multiply fractions? Multiply numerators, multiply denominators. Think of the 2 as 2 over 1. So you get 2 times 5 is 10, 10 times negative 12 is negative 120, 1 times 13 times 13 is 169. So there's sine of 2 theta. But it's the same game we did in the previous section with the sum and difference formulas. They give you information about angle, say, A and angle B. You do pictures of A and B and then use those to fill in over here to get, say, sine of A plus B or cosine of A plus B. Now, we also have to find cosine 2 theta. Well, to find cosine 2 theta, notice all three of these formulas just involve the singleton angle theta. Well, which one do we use? Well, we have a picture for theta. So we know sine of theta, we know cosine of theta, and they're all involved with theta. So you could use any one of them you want. But let's pretend we hadn't done any of this work. If you hadn't done any of this work, which of these identities would it be smart to use? We know cosine of theta, and if we hadn't done this work, we wouldn't know sine of theta. But if you only know cosine theta, it would make sense to use this one, because this has a cosine squared and a sine. This one has a sine as well, and you don't know sine. Now, we do now. But if we hadn't done this part, if it just said find cosine theta, 2 theta, it would make sense to use this identity, because this only has cosine in it. So I'm just going to use that one, and I'm going to pretend we hadn't done any of that work. So cosine of 2 theta is 2 cosine squared theta minus 1. Again, you could use any one of these because we already have the picture for theta. But if we hadn't done any of this work, this would be the easiest one to use. Okay, so this is 2 cosine theta squared minus 1. So instead of cosine theta, we can put a minus 12/13. Again, that's not theta, it's cosine theta. Remember, this means cosine theta whole thing squared. And now we just work it out. Well, how do you square a fraction? You square the numerator, 144, square the denominator of 169. And the negative, of course, goes away because the negative 1 squared is positive 1. And then how do you multiply? Order of operations, they multiply next. That's 2 over 1, so that's 288 over 169 minus 1. And I've run out of room. Okay, so I'm going to continue here. So you get 288 over 169. Well, get a common denominator. You can rewrite 1 as 169 over 169. And then to subtract fractions, we have our common denominator. And when we subtract, we get 118. So sine of 2 theta is negative 120 over 169. Cosine of 2 theta is 119 over 169. Now, a common question they will ask is, in which quadrant is 2 theta? So I know theta was in the second quadrant, but where's 2 theta? And you can't just say, oh, theta was in the second quadrant, so double that's in the fourth. No, you can't do that. Look at the answers we got. Sine of 2 theta was negative, and cosine of 2 theta is positive. In which quadrant is cosine positive and sine negative? So that's the fourth quadrant. So it does turn out to be the fourth quadrant, but not because I doubled the second quadrant for theta. Okay? Cosine is positive, sine is negative. That's in the fourth quadrant. So 2 theta is in the fourth quadrant. So that's that one. It has the same flavor as some of the ones we did in section 5.3 and 5.4. Okay, the next example says, use an identity to write this certain expression as a single number. So the expression they give here is 2 sine of 22.5 degrees cosine of 22.5 degrees. And they don't mean to just punch in the calculator around to several places. They want to get the exact value. Well, we don't know anything about 22.5 degrees, right? We don't have a special triangle for that. But what does this expression remind you of? It reminds you of this. It matches this perfectly. So I can't do anything with it written in this form, but I can, if I rewrite it in this form, what does that turn out to be? So 2 sine 22.5 cosine 22.5 is the same as sine of double the angle. So this whole expression is equal to sine of 2 times that, double the angle. But double 22.5 is 45. And notice that's an angle we know how to handle. And so that's one of our special triangles, 45 degrees. That was your 1 squared of 2. And what's sine of 45? It's y over r, or opposite over hypotenuse, which is 1 over root 2. And again, I don't care if you rationalize. Okay? So even though I don't know anything about 22.5 degrees, I couldn't do this with a special triangle. But when you realize that this is equal to this, the angle changes to 45 degrees, and that's one we know how to handle. So that one's only a 2-step problem. But the key is recognizing that matches that. The next problem says do the same thing, but this time for cosine squared of pi over 8 minus 1/2. Okay, well again, pi over 8 you should recognize is not an angle in one of our special triangles. Remember, when an angle's in radians form in simplified fractions, if the denominator is a 1, a 2, a 3, a 4, or a 6, it's one, you can get it from one of our special triangles or a quadrantal angle. Pi over 8 is not anything we can do by hand. Well, does this remind you of anything? It certainly doesn't look like these, and it doesn't match these, but it's almost the same as this, isn't it? Notice I don't have a 2 here, and instead of a 1, I have a 1/2. We're off. We're off. So I think what I would do is write down the ones I have in circles here. Let me write down the identity I know. So that's the identity I know. And this doesn't match this exactly. What can I do to both sides of this identity so that this side matches that exactly? Well, I need to get rid of the 2. So if you multiply both sides by 1/2, I get 1/2 cosine 2a. Half of 2 cosine squared a is cosine squared a. Half of negative 1 is negative 1/2. So notice I started with an identity I know, and I made a new one from it. Just like when we had sine squared plus cosine squared is 1, and I subtracted things from both sides, here I multiplied both sides by a constant to get a new identity. So this matches that. Now be careful, you cannot take half of the 2. You can't take the 2 inside of cosine, it doesn't work that way. Okay, so this matches this exactly now. It didn't match this, but it does match this. Well, by this identity, this is equal to this. So I have 1/2 cosine. Now what angle goes here? Whatever angle is here, double it goes here. So this matches this. And I started to write down the other side, but whatever angle is here, that's my pi over 8. Double it goes here, and 2 times pi over 8 is 2 pi over 8, which is pi over 4. And that's an angle we know how to do. Right? Remember, pi over 4 radians is 45 degrees. We're back to the same triangle we just had. So you get 1/2. Now what's the cosine of pi over 4? 1 over root 2. Pi over 8 is 22.5 degrees. So basically we did the same, used the same angle in two consecutive problems. So the difference between this one is the expression they gave us did not match an identity exactly, but it was close. So I wrote down the identity we knew it was close. I rearranged things to get one side to match. I said this is equal to this, which equals this. And notice the angle went from A to 2A, which was something we needed to do. So the 2 problems we just did have the same flavor. Okay. Then the last problem in this section, it's another identity problem. And it says verify the following identity. Sine of 4x is 4 sine x cosine x cosine 2x. Wow. Sine 4x is 4 sine x cosine x cosine 2x. Okay, so again, we want to start on one side and work our way to the other. You can argue the right-hand side is a lot more complicated because there's more stuff going on. You can argue the left-hand side is more complicated because the angle over here is 4x, and the angles over here are x, and 2x. So you can try to do something with the expressions, or you can try to do something with the complicated angle. Just to do something different, I'm going to start on the left-hand side. Again, write down the side you're starting on, sine 4x. Now what's my thinking here? I have an angle of 4x, but I need to get to angles of x's and 2x, so I need to make this angle simpler. Well, what do these identities do for you? Right? They can take a 2a and go down to a's. Take a 2a and go down to a's. Take a 2a and go down to a's. So in particular, I have sine of 4x, so I'm treating that as this side here. And what does this do? It tells you sine of 2a is 2 sine a cosine. Again, it doesn't have to be a 2 here. It's whatever angle is here. When you go to this side and rewrite it, it's half the angle there. So sine of 4x here is 2 sine of half of that angle, 2x, cosine of half of that angle, 2x. And it looks like we're on the right track because I went from 4x's, now I have angles of 2x's. I'm trying to get to here. Now clearly you don't want to do anything with the cosine 2x because that's what we need and that's what we have. So there's no point in doing these here, leave it alone. But what about this part? We need to make this equal to this. Well, what's the key here? This is an angle of 2x and we need angles of x's. So it looks like we need to use that double angle formula again. Here we went from 4x's to 2x's. Now we need to go from 2x's to x's. But what's sine of 2x? I already wrote the 2 down. I already wrote the cosine 2x. So what's sine of 2x? Well, it's 2 sine x cosine x. So 2 sine x cosine x. And then lo and behold, 2 times 2 is 4. You get 4 sine x cosine x cosine 2x, which is what we were trying to get to. Now, if we had started with the right-hand side and gone backwards, you'd have to realize starting here, you want to steal a 2 from the 4 and then rewrite that as sine 2x, which I think you probably could have figured out. Okay. Or just focused on the sine x cosine x, play the little game that I did a second ago, take an identity you know, multiply both sides by a half just to get the sine x cosine x. You could replace sine x cosine x with 1/2 sine 2x, and then you'd have 4 times the half would give you the 2. So I think you probably could have figured that out. But again, let me caution you about identities. You're not going to see 8 steps ahead. You just have to try something and see what happens, and then look at it like it's a new problem and see and think, well, what could I do now? And if you just get stuck, try starting on the other side. So that should get you through section 5.5.